Welcome, everybody. I had some handouts, but I apologize. I guess we didn't make quite enough. I think I underestimated the number of people in the room. But the code that's in the handout will appear up on the board here and will be in the lecture notes after class. There's more there? If there's extra copies, then let's gather them together so that who wants a handout? Pass them around over there, please. Yeah, please keep those going around to anyone who needs them. What I'm going to be talking about this week is mostly stuff for you'll need to know to do Project 2. Project 2 will go up, I think, tonight. I should be able to get it up. And it will be a project where you implement a sort of artificial intelligence that plays a game, plays a strategy game in the style of checkers or chess, although it's a little bit different than that. It's a game that involves more algorithms. But to talk about it today, I want to talk about how we do game tree search for games like checkers or chess. But to keep it simple, I'm going to stick with tic-tac-toe for now. If you're not familiar with tic-tac-toe, please Google it and learn the rules. So we want to design a program that plays tic-tac-toe. We're going to design a program that explores every possible move that you might make, and then every move that your opponents might make in response, and then every move that you might make in response to that, and actually constructs all the different grids that might be created as you go. So here's a tic-tac-toe grid. To keep it from getting too complicated, I'm going to assume that we're already 2/3 of the way through the game, and so X has placed X's and O has placed O's, and now you are the computer, and it's your turn, and you're playing X. So what moves can you make from this grid here? Well, you've got 3 different places you can place your X, and we're going to try all 3 of those and see what happens in each of those 3 circumstances. So you could place a new X at the top center, or you could place a new X at the top right, there, and you get this grid. Whoops. Or you could place an X in the bottom center, right there, and so you get this grid. So those are the 3 moves you can make, and we want to decide which one of those moves is the best move. Which one should I choose? To figure that out, well, I'm going to go ahead and look at all the different possible moves that my opponents might make in response. So in this example, on the left-hand child grid, I'm going to look at its children, which include the possibility that your opponents might put an O in the upper right-hand corner. So you get this board. Or the other alternative is O could put an O in the bottom center. Those are the only 2 choices from the leftmost grid. Let's look at the center grid as well. Actually, the center grid, the game is over because you've got 3 X's in a row, so you've won the game. So that grid is not going to have any child grids because the game is over. If we look at the grid on the far right, then that one, the game's not over yet. So O has 2 choices of where it can play its next piece. It could do it at top center, and so we get this grid. Or your opponents might go to the upper right, and so you get this grid. Now, several of these games are finished because we have 3 O's in a row here, and 3 O's in a row here. But there's 2 grids where the game isn't finished yet, so we'll give them children. Starting from this grid, though, there's only one place to go, which is you as X can put an X in the upper right corner, and that wins the game for you. And on the other one we haven't looked at that still has a child, it's the same situation. You've only got one move left. You can put an X in the upper right-hand corner, and then you've won the game because you have 3 X's in a row. So this is an exhaustive search tree for when you start from this particular root grid at the top. Now, to decide which move we actually want to make, we're going to make an assumption. We're going to make the assumption that our opponent always plays the best possible move, that the opponent also uses this algorithm, generating the entire space of all the possible grids that we might have for the rest of our game, and chooses the best move from their point of view. And if with that assumption, then you're going to use that to choose your moves. So again, we assume for now that both opponents are infinitely intelligent. So this assumption in a game like chess is usually wrong. It's usually not possible to have an opponent who's perfect chess player. But we need to make some assumption about how our opponent is going to move, and the best we can do is to assume that the opponent will make smart moves. Once we've expanded this tree, well, actually while we're expanding this tree, we want to give each grid a score. So each grid is going to be assigned a numerical score that indicates how optimistic we are about winning. And specifically, we're going to give a grid a score of 1 if the computer is guaranteed a win. So if we have a grid where no matter what move my opponent makes, I can win the game, I'm going to give it a score of 1. And the opposite of that is I'm going to give each grid a score of -1 if the opponent is guaranteed a win. Assuming, of course, that the opponent always chooses the best move. If I have an opponent who chooses stupid moves, then there's no such thing as the opponent being guaranteed a win. And finally, sometimes in tic-tac-toe, nobody gets 3 X's in a row, nobody gets 3 O's in a row, so we're going to call that a draw. So I'm going to assign a board a score of 0. If that board is a draw, the game is over and nobody has won. Or if it's a game where if both players continue to play perfectly, nobody will win. And by the way, I would usually give these constants a name, an all caps name, and make it a final static constant in Java, like computer win is 1 and opponent win is -1 and draw is 0. But to keep things simple, I'll just use the numbers today. So once we've established this is our convention, this is how we want to score all the grids, now I need an algorithm that can score all these grids. And the algorithm that we're going to use is called the minimax algorithm. Now, we don't need the minimax algorithm when the game is over. If we want to score a grid, how do we do that? If the game is over, it's easy to score a grid. If the game is not if the game's not over, that's when we have to think. But let's start with the easy case. If you want to score a grid and the game is over, let's suppose that the computer is playing X. Then if you have 3 X's in a row, then X has won the game is over, and you assign the grid a 1. If you have 3 O's in a row, then your opponent has won the game, and we assign the grid a score of -1. If the grid is full, all 9 squares have been taken with X's and O's, and nobody has 3 X's or 3 O's in a row, then the game is over and it's a draw. So we assign that grid a 0. And lastly, for any other grid, meaning any grid where the game is not over yet, we are going to need to use a minimax algorithm to compute the score of that grid. So let me explain how the minimax algorithm works. You take a grid and you expand all of its children. So in that tree that I drew at the very beginning of the lecture, you're going to take a grid and you're going to figure out all the different moves you can make from that grid and expand out a bunch of children that show what happened when you make each of those moves. And then, all right, so you consider each possible move. And for each move that you're considering, you determine the child grid that will result when you make that move. And then the next step is you assign a score to each child. How do you assign a score to a child? You call this whole algorithm recursively. Once you know the scores of all the children, you can figure out the score of the parent, because the score of the parent is going to be the score of the best child. So what do I mean by the best child? Well, which child is the best child depends on whether it's your turn or your opponent's turn. If it's your turn, you want the highest score possible, because a 1 means you win and a -1 means you lose. So you pick the child grid with the highest score. But at every other level of this tree, you're going to be looking at your opponent's turn to move, and your opponent has the opposite wishes of you. Your opponent wants the most negative score possible, and they're going to pick a move that gives the most negative score. So when it's the opponent's turn, you choose the move that yields the minimum score. And you assign that score to the parent grid. So you see that Minimax is a recursive algorithm. And if we go back to that game tree that I showed you at the very beginning, this game tree is not a data structure. We're not actually going to build a tree data structure to run this Minimax algorithm. What we are going to do is we're going to have a sequence of recursive calls, and this tree shows you the structure of that sequence of recursive calls. So we call Minimax initially on the parent grid, and that calls Minimax on its first child, which calls Minimax on its first child, and we compute the score of that grid at lower right. And then, when we're done that, the recursion backtracks, and now we call Minimax on the second child of that left child of the root, and that calls Minimax on its sole child. And then again, the recursion is going to backtrack after we compute the score of that leaf node. So we compute a score there, we backtrack, we compute a score there, we backtrack, now we can compute a score of that one grid because we've computed the scores of all of its children. And finally, we go back to the root, and now we start looking at its second child and calling Minimax on that, and so forth. So at any given time when we're running the Minimax algorithm, there's going to be a certain number of stack frames for the Minimax. The root grid is always going to have the bottommost Minimax stack frame, and when you call Minimax on one of its children, that will be in the next stack frame up on the stack. Then when that one calls Minimax on one of its children, that will be another Minimax stack frame on top of that one. And when that one calls Minimax on its child, now you have 4 Minimax stack frames on the stack. But you're never going to have, for this tree, more than 4 at any one time, because this call to Minimax backtracks, gets popped off the stack, before we go on to the next call to Minimax. So again, the bottom line here is that we do not actually build a tree data structure. This tree shows us the sequence of recursive Minimax calls, and each one processes its children in order from left to right. So let's start scoring these. So to score the root node, you have to score all 3 of its children first. And to score the leftmost child, you have to score both of its children first. So when the recursion gets down to this grid here, that's the first one we can actually assign a score to. And since we have 3 O's in a row, that is a win for the opponent. And that means that grid has a score of -1. To figure out the scores of nodes higher up in the tree, you need to know whose move it is, because every level is going to be a min level or a max level, depending on whose turn it is. So at the top level, when you go from the root grid to the children, these are all computer moves. And whenever you're doing a computer move, you look at all the different children, you compute their scores, and you take the maximum. So you can think of this bunch of arrows as being a max level, where we're going to look at the 3 children, look at their scores, take the maximum, that's the parent's score. The second level of the tree, this is the opponent move. Let's just call it a human move for short. Suppose that your computer is playing against a human. And so these 4 arrows all pointing down represent a human move, and since the human wants the lowest score possible, this is going to be a min level of the edges of the tree. And then again at the bottom, we're going to have a computer move for some of these grids, if the game isn't over. And so this will be another max level of the tree. And if you had a much deeper tree, it would keep alternating between max level, min level, max level, min level, max, min, all the way down. So, that grid on the far left got scored first. It got a -1 because the opponent has 3 O's in a row. After scoring that grid, we'll go to score this grid next. We can't score that grid until we score its child. The child has 3 X's in a row, so that grid gets a score of 1. That's a computer win. And the score of the parent is the maximum score of all its children. It only has 1 child, so we're going to have to take that score. But this grid gets a score of 1 as well. Now we go back up the tree because we're backtracking the recursion, and now we can compute the score for that grid there because we've computed the scores for both of its children. This is a human move. The opponent is moving against you. The opponent's going to choose the minimum score possible. It has a choice between a 1 and a -1, so it's going to pick the -1. Obviously, it wants you to lose. And so that board isn't a very good one. If you get to that board, you're going to lose the game. But we have a few other ones we can investigate. We backtrack now to the root. We've scored its leftmost child. Now let's score its second child. So what is the score of this grid here? Well, that grid has 3 X's in a row, so that is a win for you. So that gets a score of 1. And we're done, because the game's over there. So now we're going to go on, backtrack to the root node again, and now we're going to score its rightmost child. To score the rightmost child, we need to go down and look at its children. So we'll go to this one, and to score that one, we have to score its child. So we go down to this one. And the score of this one, again, there's 3 X's in a row. So this is a winning grid for the computer, and we will give it a score of 1. And its parent gets a score of 1 because we take the maximum from all its children. Then the recursion will continue on and look at this child next. That child has 3 O's in a row, so that's a win for the human, and that grid gets a score of -1. Now we can backtrack the recursion and assign a score to their parent. Again, this is a min level. The human moves, so we take the minimum of the scores of those 2 grids, and that's a -1. And so this grid gets a score of -1. And finally now we can score the root node. The root node, well, this is a computer move, so we take the max of its 3 children's scores, and the maximum is the middle one, so we're going to assign this grid a score of 1, which means that the computer has a winning move. And more importantly, now we know what the winning move is. We know that the computer wants to choose the middle grid and not the left or the right moves. The left or the right moves are losing moves. The middle move is the winning move. That's the one we pick. And that's how the Minimax algorithm works. Any questions? Yes, in the back. If at the bottom row, what? If at the bottom row there's a grid where neither side wins and the game is over, then you assign that grid a 0. And the min and max rules work just fine if you have zeros as well. So you can mix ones, minus ones, zeros. The min and max rules are still the correct rules. And in fact, we'll find out later that you can mix a whole bunch of different values, not just 3. Yes? Yes, we sure could make this algorithm more efficient, and I will talk about that in 1 minute. But let me get the rest of the questions, and then we'll go on to that. Near the back here. I'm sorry, can you talk a little louder, please? Like if you what? Oh, if the opponent is somewhat stupid. Probably you can make him to max adapt to that, but it's not easy. You have to have a good model you have to have a cognitive model of what kinds of mistakes your opponents make in order to exploit the kinds of mistakes that your opponents make. And that's not an easy thing to do. That's definitely an advanced topic. But yes, it can be done. Yes, over here. If you have 2 or more winning moves, then, pardon me, got it, I'm getting over a cold here. If you have 2 or more winning moves, then it's pretty much arbitrary which one you choose. You could pick any one and it'll be good. You have pseudocode in front of you, which I'm going to go over in a minute, and that code happens to always pick the first one that it gets explored. So whatever order you generate the moves in, the first winning move is the one that will get picked. All right, so let's take a look at this code that is in the handout. Again, apologies to those of you, any of you who didn't get one, but this code will be in the lecture notes, of course. This is a method called chooseMove that implements the min-max algorithm. And the idea is that it has as its input a parameter side that tells you whether it's the computer's turn or the opponent's turn. What its goal is to return an object, which we call a best object. A best object is just an object that contains 2 pieces of information, namely the move that you've decided to make and whatever score is assigned to that move. So we're going to return an object that looks like that. This is the move I want to make. This is the score that this move has. The code starts with the base case, which is all of the cases where the game is over. We return a value, 1, minus 1, or 0. This is pseudocode, by the way. It's not all fully written out Java code. But most of it is Java code. If the game is not over, then we have to pick a move. So what we're going to do is we're going to initially set the score to the most pessimistic score possible. And what pessimistic means depends on whether it's your turn or your opponent's turn. If it's your turn, then we set the score to -1, meaning if I can find any move that gives me a score of -1 or better, I'm happy at this point. And if it's the opponent's turn, the opponent is pessimistic by assuming the score will be 1 unless the opponent finds a better move. Just to make sure that move always gets initialized, I'm going to assign move to be some arbitrary move. The reason we need this line of code is it is possible that all of the moves will be losing moves. If all of the moves are losing moves, you still have to force the algorithm to pick some move. Doesn't matter which losing move you pick, but pick one. But otherwise, the heart of Minimax is going to be this loop in the middle that goes through every possible legal move. So we're going to try out every single move and assign each move a score, and then pick the best one. And to assign things a score, then the way this code is set up is, because it's slow to copy the entire grid, we're just going to have one tic-tac-toe grid object, and we're actually going to modify it so we perform the move, but then we unmodify it after we've computed its score, which brings us back to the current grid. But when we modify the grid, then we have a recursive minimax call here. So this is the heart of the recursion. And so the idea is we're going to use minimax to score all the children and get scores from the children. And then, for each child, if the child is better than all the previous children we've seen, then we pick that child. And so So this just says, if the new child is better than all the previous children we've looked at, pick the new child. The if conditional is a little bit complicated because the meaning of best child depends on whether it's the computer's turn or the opponent's turn. If it's the computer's turn, you're looking for a new move with a higher score than the previous best move. If it's the human's turn, you're looking for a child whose score is lower than the previous best move. But if you find one of those, then you go ahead and you update the move object, that box I drew in the upper left, to have the new better move and the new better score. And then when the loop is done, you just return the best child that you have found. And so that's how Minimax works. And again, I just want to remind you that each grid in the game tree that I drew at the very beginning of the lecture represents one call to this method. And again, each grid constructs its children and processes them in order from left to right. Any questions about the Minimax algorithm? You always start this at whatever board you're actually physically at now. So you assume you've been playing the game for a while, you're at some board, you want to make a move now, you take the board as it is right now, and you use that in the root call to this method. At the beginning of the game, you would have a totally empty grid. Choose randomly? What do you mean by that? Well, no, you're actually going to try all 9 possibilities for X. You don't pick X randomly in the grid. So at the very beginning of the game, you have an empty grid. There are 9 different places you could put X. And if you run Minimax, it will notice things like that if you put the X on one of the side squares, not a corner or the center, then you're going to draw instead of winning the game. So you shouldn't pick those ones. If you put the X in the center or in a I think if you put it in a corner, can you win the game? I don't remember. If you put it in the center, you can definitely win the game. Corners, I'm forgetting. Other questions? Yeah. Pretty much. So the question is, suppose I run this on a grid. I finally, after expanding this tree, figure out the best move, and I make that move. Now my opponent makes a move. It's time for me to move again. Do I have to redo the whole tree from scratch? Well, yes and no. Usually that is what's done. If you really did do the entire tree for an entire game, then you wouldn't have to. You could maybe keep the information in this tree and reuse it on the next move. But for realistic games like chess or checkers, where you cannot expand the whole tree, you really do have to start over from scratch every time it's your turn to move. So next I want to talk about how to make Minimax more efficient by doing various kinds of pruning. And to motivate it, I will start with what's called simple pruning. And the idea is pretty obvious, and one of you already asked me about it. Suppose that you are going through the children of a grid, and a player discovers a guaranteed winning move. Well, if that happens, then there is no reason to go looking at the rest of the children. You've got a winning move. You don't need two winning moves from the same grid. So how do we put this into action? Let's go back and look again at the tree that we already looked at. So if you look at this tree, consider when you are evaluating this particular grid. It has two children. We expand the left child first, and we see that this grid has a score of -1. And since it's a human move, the parent grid is going to have a score that's the minimum of all its children. So that means -1 or smaller. And you can't go smaller than -1. You already know, hey, this is a winning move for the human. There's no point in looking at this move at all, because you can't do better than winning. So that means that if you do simple pruning, you can just skip this. You don't have to compute scores for either of those two grids at all. You can just say, the human is going to pick this move, and that's that. We're done. The same thing happens again later, one step higher in the tree when it's the computer's move. The computer looks at its first child grid and says, no, that's a sucky move. I don't like that. I lose. Then it looks at the second move and says, oh, there I win. So I'm going to make that move. I've got a winning move. Don't need to look at any more moves. So this whole subtree can go away as well. Don't need any of this because I've already got a winning move right here. And that's how simple pruning works. And in practice, it can save you a lot of time. Question? So that's a good question, but it's an advanced question. The question is, if you do this, pruning, the order in which you check the children matters a lot. What you'd ideally like to do is check the best move first, find out that it's a win, and then you don't have to look at the other moves. If you put your children in the wrong order so that the winning move comes last after all the losing moves, then you're going to spend a lot more time. And so what you'd like is to have heuristics that can guess which moves are likely to win and which moves are likely to lose. And you might want to investigate that when you're doing Project 2. Having said that, it's an art, it's not a science, and so you can try to guess which moves will win and which ones will lose, but you can't know for 100% sure without actually doing the full minimax tree expansion. So instead, people design heuristics that try to guess which moves are more likely to pay off and try those moves first. Yes? Breadth first search instead of depth first search? It's somewhat limited. I mean, you can do something like a prioritized breadth first search where you expand tree nodes in order according to which ones you're most optimistic about. But that's a really advanced topic, so I'm going to leave that aside for now, and maybe you can ask me about it again when the project's underway. Oh, one other thing I should say about simple pruning is that sometimes a winning move, not all winning moves are equal. If you're playing chess, it's better to win in one move than to win in 3 moves. If you have a move that will win now, and you have another move that guarantees you will win on your next turn after the opponent plays, you should pick the move that will win now. And so think when you're doing your project, do keep that in mind. When you're doing pruning, you don't necessarily want to prune away things just because you found a win in 3, because you might find a win in 1, and that's better. But what we're going to do in the project is a more sophisticated version of pruning called alpha-beta pruning. Alpha-beta pruning subsumes simple pruning. In other words, it does everything simple pruning does and more. And to try to motivate it, I'm going to use a more complicated tic-tac-toe example. So here's another example where we filled in we filled in 2/3 of the game. We've filled in 6 squares, and we've got 3 left to go. But this one isn't really the win-lose kind of grid that the other one was. This one, if the players are smart, they're pretty much guaranteed to tie. So X has several choices. Make a move in the right center square, like that. Make a move in the top center square, like that. Make a move in the bottom center square, like here. And from those, we can expand out further. So from the left child, there's 2 different moves you can make. O can put 1 in the top center, or O can put an O in the bottom center. And from those 2 grids, now we're going to go down, and it's X's turn again. And X fills in the last remaining square. So that's what the whole left subtree looks like. Let's score these grids. The bottom left grid, nobody has won. The game is over. So this grid gets a 0. The sibling of that grid, same situation. There's no 3 X's in a row, no 3 O's in a row, so that grid also gets a score of 0. As we look at the tree, we want to know which ones are the min levels and which ones are the max levels so we can score it. Well, the computer move goes first. So the computer move level is a max level. Then it's the opponent's move. So the human move level is the min level. And then it's the computer's turn again. So that third level is going to be a max level. Now we're going to give scores to these two grids by taking the max of their children. Each of them only has one child, so their scores are 0 as well. Then we score the parent of that by taking the minimum of its children, and both of its children are 0, so the minimum is 0. So what that means is that this whole subtree of the tree, if we make that first move, the game is going to be a tie game. Nobody's going to win. So that's the first move. Let's try this. I'm going to just call that grid A so that we have a name for it. Now I'm going to call the next grid the sibling grid, which I'll call grid B. And A is a tie. We're hoping that B will be a win so that it'll be better than the tie. So what happens? Well, we look at its first child. Let's suppose that O goes in the bottom center. So that's the move. And then it's X's turn. X puts an X in the last remaining space, and nobody has won this game either. So this grid gets a score of 0. Its parent grid gets a score of 0, the maximum of its children. And now, well, we haven't expanded all of B's children yet. There's another child that we can look at, but we know something about B's score. We don't know everything about B's score, but we know B's score is less than or equal to 0. Why do we know that? Because this is a min level. This is the human's turn. And so when the human makes a move, it chooses the min of all of its child grids. One of those child grids is a 0. The min of 0 and some other values that we don't know yet is 0 or less. It could be a lot less than 0. It could be a losing move. It might be a tie move. We don't know yet. But what we do know is that move B cannot be better than move A. Move B has a score that's less than or equal to 0. We don't know what its score is yet. We just know that it can't go higher than 0. Move A, we know, has a score of 0. So it is impossible for move B to be better than move A. It could be worse. It could be much worse. We don't know how much worse. We don't care because we know that move B cannot be better than move A, and therefore there is no point at looking anymore at move B. So bottom line is we don't finish calculating B's score. We just notice that B's score is less than or equal to 0. Therefore, move B can't be better than move A. Therefore, we stop. There is no need to waste time computing the score of this child because move B can't be a better move than A. So having done that, now we skip ahead to the next sibling or the next child of the root, this grid C, and we'll do the same thing with grid C. We will try one move. We will see what happens if O plays the top center, and then we get this grid. And then the child of that, X, has to play here, so we get this grid. And once again, nobody has won the game. It's a tie game, so this grid gets a 0. Its parent grid gets a 0. And we know that C is the min of all its children, so C has a score less than or equal to 0. So just like with B, we know that C cannot be a better move than A. It might be worse. It might not be worse. We don't care. We're not going to waste the time to find out. So So we've got this intuition here that once the computer discovers a move that guarantees a draw, then from now on, the computer is only interested in looking at moves that are better than a draw. So suppose that the computer is investigating a different move, an alternative to A. Call that alternative move B. And while investigating that move, it discovers that if the opponent makes another move in response, I'll call it move X, then the opponent can force a draw. So X, by the way, is this grid right here. The first child of B is called X. So we discover that if the opponent makes move X, the opponent can force a draw. So it's a waste of time to continue investigating B. So what we want to do is we want to turn that insight into an algorithm. So alpha beta search does that by establishing two scores, alpha and beta. Alpha is a score that the computer knows with certainty it can achieve. By choosing a better grid. And beta is a score that that the opponent knows that it can achieve. And the general rule is that if beta becomes less than or equal to alpha, then further investigation of the current grid is useless. And so to see how that works with the grid we had up top, what we do is we always start the root grid with alpha equal to -1 and beta equal to 1. And we pass those values down in our recursive calls. But when a value gets returned by a child grid, for instance, when this child grid here returns a 0 to the parent, that return value modifies either alpha or beta, depending on which one is, whether it's the computer's turn or the human's turn. And so in this example, when it's the computer's move, alpha is going to change from 1 to 0, as a way of saying, here's a move that guarantees a draw. At the next level up the tree, we pass a 0 back, and here beta changes to 0. At the top of the tree, we pass a 0 back, and alpha changes to 0.